Oh, sorry, Jacqueline. I just saw the your message. How many people are we expecting, more or less?
I think there are 42 signups.
Okay.
We have 35 people so far.
Yeah, then we can probably start.
Okay, I should just let everyone know this is being recorded. Great, off you go. Thanks.
Great, thanks, Jacqueline. So my name is Ferran Brossa Planella. I'm a research fellow at WMG at the University of Warwick, and today I'll be stepping in to give this first Faraday Tech on PyBaMM. Robert will join us. He's around to answer questions, and he'll join us for the session next week. He'll deliver it. So the session today is a brief introduction to PyBaMM. What are the main capabilities of this package? And next week we'll go into detail into more advanced features, and we'll demonstrate through 2 case studies that they've actually turned into papers, or they've been used to produce results that turn into papers. So hopefully what we present in these 2 sessions will help you to be confident enough on using PyBaMM so you can use it for your own research. So the first thing to use PyBaMM, of course, is that we need to get PyBaMM installed. And sorry, before I go ahead, just let me mention that PyBaMM is as an open source package, so has contributions from many institutions. It's mainly funded by the Faraday Institution through a lot of partner institutions. So there's University of Oxford, University of Michigan, UCL, Imperial College, and WMG. So as I was saying, the first thing we need to do to use PyBaMM is to get it installed. So the instructions are slightly different whether you're using Linux or Mac or Windows. So if you're using Linux and Mac, they follow very similarly. And actually, the detailed instructions, you can find them in our website, and then you can follow a link that will bring you the page where everything is detailed. But basically, it is running these 3 commands you have here. You need to have Python pre-installed. You might need to have the package called will pre-installed, otherwise it might throw an error saying that will has not been found. But basically, then you run Python and you create a virtual environment. A virtual environment, you don't need to worry much about that. The only reason to use that is because PyBaMM requires certain packages to be certain versions, and if you have several of projects that might have different requirements, they might conflict. Using a virtual environment prevents that from happening, so it's safer. And then you activate the virtual environment. That's the second step. That's basically telling your computer, now I'm working on this virtual environment, so ignore everything that lives outside of it. And then you can just type pip install PyBaMM, and it will download the most recent version, which is now it's version 0.2.2, which was released yesterday. Let me make a live demonstration on how to do that. And to do so, here you have is my terminal, which is it's in Windows, but actually it will behave like Linux. So first, I will go to the folder where I want to install that. So the one I created for the Faraday Tech session. And now, first, I need to create the virtual environment. So I will type this. I'm not going to hit enter because I already created my virtual environment and that might conflict. But basically, you hit enter now and sorry, Python 3. And it should create a virtual environment. Once this is done, let's go to the second step. So I need to activate this virtual environment. So notice now that in front of my line, there is this brackets env, means my virtual environment is activated. That's very important. So every time you want to use PyBaMM, you'll need to activate your virtual environment. You can easily check if it's not activated. Otherwise, you'll get an error that says PyBaMM has not been found. Alternatively, if you want to exit the virtual environment, you can just go deactivate. As I said, the detailed instructions are on the link in our website. And if you are having any issues running that, just drop a message in the Slack channels, and there's other people from the Faraday team that will be able to help with that. So I'm now in the virtual environment, and finally I do pip install PyBaMM. Now it will probably run faster in my computer because I already have all the requirements satisfied. So these are all the packages that PyBaMM needs in order to be able to run. So that was pretty quick. In your computer, it might take a bit longer, but basically, after you let it do all the installation, and after all, you get successfully installed PyBaMM 0.2.2, which means that now you're ready to use PyBaMM. Now, let me go back to the presentation. As I said, Windows is slightly different. So you see the instructions look very similar, but they're not quite the same. But again, in our website, you can find the detailed instructions on Windows. Before doing the demonstration, just let me say that the basic features are ready to go in native Windows. But if you want some of the advanced features, like extra solvers, we recommend using Windows Subsystem for Linux. The instructions are online as well. Basically, what it means is that you create an subsystem in your computer, as the name says, and then you can use all the Linux commands, and your computer will translate it for Windows to understand them and run them. So it's basically having a window in your computer, which is in Windows, but that actually understands Linux. But for the session today and next week, that's not necessary. So if I don't know how many users are using Windows, but they'll be fine with the basic Windows features. And before going ahead, let me demonstrate how to do that on Windows. So hopefully you can see my terminal now. It looks similar to the one I showed earlier, but now that one is the Windows command prompt. You can find it by typing CMD in the search bar next to the Windows icon in your bar, and that will launch one of those black windows. And basically, first what I need to do is go to a folder where I want to install PyBaMM, and everything will be in there. So in my case, I already created one called PyBaMM. So I'll go there. By the way, if you're not familiar with these commands on how to change folders and so on, you can use, in the installation instructions, you can find a link to a page where the main ones like change directory, create a new directory, see what's in your directory, and so on. You'll find this syntax. But basically, in order to create your new folder, you can do it as usual. You open your Explorer and you create a new folder, and then you just need to navigate there. So in my case, cd PyBaMM. And as you can see now in this PyBaMM folder, and now I can go ahead with the installation instructions I showed earlier. Sorry, So first, and I already have Python installed, so I create my virtual environment here. And now I'm actually creating it. So you'll see it takes some time to create this virtual environment. And again, the idea for that is the same as for Linux and Mac. We don't want whatever we install here to mess up with other packages we might have installed. So now that the virtual environment has been created, as you can see, I can type again. The command is slightly different. So we need to go to env /scripts/activate.bat. And notice that if you're not familiar with that, Windows uses backslashes and Linux and Mac use slashes. So that might be confusing. And now notice that again, I get this here, this virtual environment activated, right? So I see that in brackets I have env. And now I can just type pip install PyBaMM. And here you can see it's going to take longer because here I didn't have any of the prerequisites, so it will have to install all these packages. So it might take 3 or 4 minutes, depending on how fast is your internet connection when installing that. So before going any further, because we would like people to be able to follow the tutorials we're going to give, just let us know on the Slack channel if you've had any issues installing, so we know if we need to, we stop for a while and we help people getting up to pace, so we can just keep going and install. Right. Yeah. Also, a very good point that I've just seen on the Slack channel is that you can use Conda if you are more familiar with that. So you can actually install PyBaMM using Conda as well. For those who are not familiar with Conda, that's fine. It's similar to the virtual environment, so you can install all the things without conflicting with others. Right. So what we can do, seeing that there are not any questions so far, is I'll continue with the presentation because first we want to give an introduction on how PyBaMM works and how it is designed. And meanwhile, if people are struggling with the installation, they can just let us know on the Slack channel. And hopefully by the time we get to the exercises, people have have PyBaMM installed and they can follow. Right. So let's go back to the presentation. So first of all, you might be wondering, what is PyBaMM? So the idea is that PyBaMM is this framework. So you can create your battery models and solve them. And the ideas or the ideas when designing PyBaMM is that we want it to be fast, flexible, and modular. So fast, of course, we want to get our simulations as fast as possible because in many applications, it's not just a matter of running one simulation and that's it. If you want to do parameter fitting or optimization and so on, you want to run a lot of them. So you want that to be fast. We want it to be flexible so people can add a lot of new features. So if you say, oh, I like to run the DFN model, but on top of that, I want to put some specific thermal model or some specific degradation model, that should allow for that. So it's like choose the different features, and that brings us to being modular. So the idea is that all these models are made of submodels, and then you can change one specific piece of the model, and everything is consistent, which saves a lot of time when, for example, as I said, you want to say, I want to run the DFN model, but I want to try this new electrolyte model that I've developed. You don't need to code everything again. You just code your electrolyte model, and then you just change that into the standard DFN. We'll see more on that later. But the good thing is that many of these standard models that people use are already in PyBaMM, so you can easily run simulations of them or do some tweaks on it. So for cell geometries, we have 1D, the 2+1D single layer pouch cells. So that's basically having a pouch cell. So you have a 2D problem for the current collectors and then a 1D problem for the cell thickness. In terms of standard lithium-ion models, we get the OD model, that's for fast diffusion. We get the single particle model with electrolyte, Doyle-Fuller-Newman model, which is also, you might know it by the name of pseudo two-dimensional or P2D model as well, plus lead-acid models. So all of these are already in PyBaMM, so you don't need to code them again. You can just, as you'll see, with very few lines of code, you can get them up and running. We have some chemistries already inbuilt, even though you can, because it's flexible, you can add your own very easily. So for example, we have LCO, lithium nickel, cobalt, oxide, NCA, graphite, LiPF6. And you can, it's again, one line of code to change from one to another and compare. So you can also do fully coupled thermal models. So because it's modular, you have your electrochemical model, which you can choose from the ones above, but then also you can have some thermal model on top of that, and PyBaMM will take care of making sure that the heat sources are defined properly given your electrochemical model. And another feature that I think you might find very interesting is the experimental suite. So in many cases, you have your simulations defined in terms of an experiment. Like, okay, I want to do a 1 CDS charge until I hit 2.5 volts, and then I want to stay there for 2 hours, and then I want to charge again up to 4.2 volts, hold it at 4.2 volts until the current gets some limit. So if you do experiments, you're probably familiar with all this language because that's how you set up your experiments. But the problem when doing modeling is that if you have your model and you need to prescribe the applied current, that might be very tricky. So PyBaMM allows you to pose the experiment in a very simple way. It's actually typing it in words, even if you are explaining someone how you want the experiment to be run. And that's very easy to define new protocols. For example, if you wanted to do a Git test, you would just say, do a discharge at a given C rate for that long, then wait for a couple of hours, and then repeat that as many times as you want. And we'll see an example later, but that's very straightforward to run. We can get nonlinear parameters as either given a functional form or data. For example, the very clear example of that will be the open circuit potentials, right? So in the battery models, we have some parameters that are just a number, but some of them are a function. For example, the open circuit potentials are a function of the stoichiometry of each electrode. So you can provide that either with a function that you fit it, so you define that function, or as data, and then PyBaMM will interpolate through the points for you, and you don't have to worry about that. We can have structured electrodes, so with different particle size as you go through the electrode thickness, and you can interface PyBaMM with external software. So there are a lot of features that are available that hopefully meet your needs on the simulations you need to run. And here's an example on the flexible submodel structure. So you can think of the battery models being built from submodels, right? Like a Lego blocks, right? So the Doyle-Fuller-Newman model will have a model for the electrolyte concentration, actually, which needs to be consistent with the electrolyte potential, so that we can consider that one submodel. But then you're going to have one model for the lithium transport in the particles, and one submodel for what's the charge conservation in the electrodes. And also you can have a submodel on what's the chemical reaction, because maybe you don't want to use Butler-Fulmer. So as you can see here, what PyBaMM does is have all of them defined separately, and then it brings them together to create your custom model. So you can just change one of the blocks and keep going. The good thing is that allows for this plug and play physics. So here you can see that you can easily compare two different models. So here we're comparing the standard DFN with the particle distribution DFN. So you can see here what's the particle distribution. So they not all have the same size, but actually you have bigger particles near the separator. And actually, again, that's something that's already in PyBaMM and you can use. So if you're interested in what happens behind the scenes, that slide is for you, because the way PyBaMM is defined is that you create your model, and actually when you define your model, you do it in a very high level language, right? So basically you write it as if you were writing a differential equation. You say, okay, I have du dt equals some divergence of this thing, which is a diffusion coefficient times the gradient of my variable. And then PyBaMM stores your model this way, which allows that then when you provide the parameters, it will plug them in, so you can change the parameters very easily. But more importantly, when you go to the next step, which is defining your mesh and discretizing your system so you can solve it, it will take care on what does gradient mean and what does divergence mean. So if you are in a one-dimensional model, it will just plug the dx here and go ahead. If you are in a cylindrical domain, it will plug whatever needs to be for the gradient and divergence in a cylindrical coordinates, which means that you don't need to worry about discretizing, meshing and discretizing properly, because PyBaMM will take care of that. And also it means that you can change geometries very easily from one to another. Imagine you, instead of, for example, in the particles, you have spherical domains, but let's say you wanted cylindrical particles. You could easily change that. And then you just pass that to the solver, and later when it's solved, you can just do all the post-process and visualization very easily. So it's very easy to extract variables and plot them, as we will see later. In terms of spatial discretization, you can choose finite volume methods and also finite element method in 2D, but now this is currently supported on the current collectors for the pouch cells. But again, because it's modular, you can add your own discretizations very easily. Another good feature of PyBaMM is that it calculates the analytical Jacobian from this expression tree. And that's quite important, because when you're solving your problem, if you know this Jacobian, and don't worry if you don't know what the Jacobian is, but basically it's something you calculate from your model. And if you know that and you can evaluate it, you can go much faster when solving your system. It's actually orders of magnitude faster. And then also you can easily change your solvers depending on your problem. So that's be the block down here. And the final thing to say here is that you can set up and perform sensitivity analysis, which is quite interesting because then you can see which parameters are more affect your output more compared to the others. So just to show you, and we'll do that in the examples later, but as an example, if you just want to do some constant current discharge, well, you only need these 5 lines of code. So you define your model, you create a simulation, you solve it, and you plot it. And then you get this interactive plot, and you can move this slider and go back and forth and see how things evolve. So it's very easy to, if you want to investigate on what happens if I change this, what happens if I change that, it's very straightforward to do. If you want to change the parameters, as we said, some of the parameters are already there. So you can just change them easily by calling them. Next week, we'll see how you can define your own parameter set, because we thought that that's something that you can find very useful. The experimental protocol, as I mentioned earlier, you can just tell PyBaMM, look, I want an experiment that starts by discharging at C/10 for 13 hours or until you hit a given voltage, in this case 3.3 volts. Then you rest for 1 hour, then you charge at 1 ampere until 4.1 volts, hold there until you reach 15 milliamps, and finally rest for an hour. And then you take the whole block and you do it 3 times. And that's basically what you get with the terminal voltage. So that's very powerful because it's not only that you can define a current, which is what you would easily define in your model, but you can define a certain hold at certain voltage, or even you can charge at a given power. So all of these are, you can just choose and play and get whatever experiment you want. And in terms of how fast it is, well, here we have a comparison that was run in a laptop. You can see the specification down here, comparing the single particle model and the Doyle-Fuller-Newman model. And that's each row is different number of grid points per domain. And of course, the Doyle-Fuller-Newman model, the way it's defined, grows much faster. So you can see the complexity of the problem by the number of states. But still, that's pretty good job. That's for 1C constant current discharge. And you can see that the SPM runs in, a few milliseconds. And the Doyle-Fuller-Newman model, even with quite big problem down here, you can get it in 4 seconds. In terms of different solvers, we have these Casati solvers both on fast mode and safe mode. You can see it still does a pretty good job. And then there's the IVA KLU and Scikit-ZAE. Scikit-ZAE wasn't able to deal with such big problems, but again, depends on what you want to do. You might want to change them. So it's always good to be able to choose from different solvers. And PyBaMM allows to use drive cycles, as we'll see in the example later. So of course, drive cycles are much harder to simulate, as you can see here, but still with the Casati fast mode. And the difference between fast mode and safe mode is fast mode won't track if you hit any events, like if you hit any critical voltage or maximum concentration and so on, but you can get it in 4 minutes, which is quite good speed. Right, so it's time for the live demo. Let me check how things are going on Slack. So if people have any questions, let's stop before we go to the live demo. Feel free to ask any questions either on Slack or unmute so you can ask. Oh, sorry, I just saw that there are some questions here on the MS Teams, but they seem to be dealt with. Right, so let's now, let's now see how we can run the example. So you can find, and let me share the link now. You can find all the notebooks that will be running here. So that's on PyBaMM GitHub. And just let me show you, I'll post the link here so you can easily find them, but all the notebooks are available here, so you can just download them and use them on your computer. Just let me post the link on here in the MS Teams chat. But now, and I think that's one of the questions that came up. Just let me show how I can launch the notebook. So basically, what I would go is I'm now on this Faraday my folder where I installed PyBaMM, right? And what I'm going to type is Jupyter blank space notebook, and then all of this appears. There's a chance that that launches a browser tab, and you already get there for the Jupyter notebook. In my case, because I'm in Windows Subsystem for Linux, won't do that for me. But then you just need to copy this line over here. It says that localhost colon 888. You copy that, and then I'll just go. Let me change again. I'll just go to my to Google Chrome, my browser, paste that, and that basically brings me to my Jupyter notebook environment. So let me see. I think there was a question. Cool. So let's start first with the first example. As I said, I'll be typing it live, so I can go step by step. But you can find the whole notebook here. So up to you if you want to just run each cell on the already created notebook, or you just want to type along with me. So I'm going to create a new notebook. I'll choose the one with the virtual environment, so it knows where to find PyBaMM. And what we're going to do first is run a simulation. Remember, I said you can run your simulation with only 5 lines of code. So let's see what are these first with these 5 lines. So first, we need to import PyBaMM. So we need to tell Python that we want to use this package, otherwise won't know where to find it. The next thing is to tell PyBaMM which model we want to use. So we type pybamm.lithium_ion and then we choose. So now I'm going to choose the FN, but I could just type instead of the FN, I could just do the same, like pybamm.lithium_ion.spm or spme, and that would do choose the other model. Along the tutorial today, we'll be using different models, so you'll be able to see all of them. So now that we have decided which model we want to use, we're going to create a simulation. So simulation, basically what it does is run, as I said, a simulation with everything by default unless otherwise specified. So the minimum you need to tell simulation is which model you want to run the simulation on. So in this case, it's the basic one. We say we want to simulate the DFN model that we defined before. And we just, with the default parameters, default discretization, default solver, default experiment, which in this case is a 1C discharge. So we hit that, and you could see that that was pretty quick because we just defined it. Now we need to solve it. So now we take this sim, which is our simulation, and we say .solve, and that will actually solve that simulation. So that created the simulation, but actually that's not very helpful, right? The output says it's a solution to your simulation. If we want to see, we like to see a plot. So then what we can do is say sim.plot, and I will plot the solution to that simulation. So that's basically the default plot that shows you the most important variables on the simulation, right? So you have the particle surface concentrations, the electrolyte concentration, what's the current and voltage, and the potentials. Now, in this slider, you can just change what's time. We've noticed that in Jupyter notebooks, that slider lags, right? So you change it, and it takes a while to update the plot, and it can be significant. So we are aware of that, and we're going to fix it as soon as possible. But just to show you how that should work, let me show you the plot if I run it locally on my computer rather than the notebook, to see how this should look like. So here you can see it that's on my computer when I run it as a script. And as you can see here, you can easily update it. So the ones that are just a variable that depends on space, it will plot at each time. And for this one, we see this dash black line that tells us at what time we are at the moment. So that allows us to very quickly see what's going on in our simulation. Right. So I'll go back to my Jupyter notebook. And of course, it's very handy to be able to plot so easily, but maybe you say, well, actually, I don't want to see all these variables, and I want to see one, or I want to see one that is actually not plotted here. So first, we need to know which variables are available, right? So you can type model.variables, and it will show you all the variables that are available. That's a pretty long list, as you can see, because there are a lot of variables defined there, and also they are both in a dimensional form, dimensionless form. For example, for time, you can get it in dimensionless form, so time here, no units, in seconds, in minutes, so that can be quite confusing. That's why you can do something, sorry, just working with two computers, which is not the easiest, but what you can do is search for a specific variable or for a specific word in the variable, and then PyBaMM will tell you which variables have this word in it. So what you can do is, there we go.
I'm sorry, is it any chance to see top of your notebook?
Yeah. Actually, if that helps, I'm I'm following what's called what's notebook 1 in the link I sent in the MS Teams chat. So basically, I'm going line by line there. So if you at some point you want to go back and see what is there, you can see it from that link as well. Is that fine? Shall I go ahead?
Yes.
Cool. So as I said, that's a very long list, and it's hard to get through and find what you want. But what you can do is model.variables.search, and then you just put here in between inverted commas what you want to search. So let's say I want to plot the electrolyte concentration, but I don't know how to properly how it's defined, right? How the variable is called. So I just say electrolyte. Then it will throw all the variables containing electrolytes. So as you can see, that's still a long list, but much easier to find. And again, you can see that it's defined in different units for convenience. So if you just want a dimensionless version, or in molar or moles per cubic meter. So now that we know how to find our variables, we can actually tell the plotting function that we want to plot specific variables. So let's say I want to do simulation.plot, and if I run it now, it would run the default ones. But I can pass here as an option a list. So lists in Python are defined between square brackets, and I'll pass for example, electrode current density with no units because I want to see the dimensionless version. And then I want to see as well terminal voltage. And for example, now I want it in units, so I pass it in volts. And again, notice that what I'm passing are what is called strings. So it's all between inverted commas. Otherwise, you'll get an error here. And the cool thing is that PyBaMM will automatically see how many variables you pass and will produce a nice plot for you. So for example, here, you can see it's only 2, so obviously it's side by side. And here it's plotting the electrode current density and the terminal voltage. But you can do even more. What you can do, and just let me copy this one, is put nested lists. That is a list within a list. So, and what will that do is that we'll plot variables on top of each other. So for example, let's say we want to plot the electrode and electrolyte current densities on top of each other to compare, and then terminal voltage. So the first element on this list is going to be another list. And that one is what do we want on the first plot. So electrolyte current density. And then the second component on that list is the terminal voltage. So that would be the second plot will remain the same. So if I run it now, notice that PyBaMM created the first plot with two different curves. And here the legend tells us is the electrode current density for the solid one, and the dotted one is the electrolyte current density. So basically, you can very easily plot whatever you want to see, and plotting on top of each other is much easier to compare, because as we'll see later, you can do that for different models. So you can easily compare different models. Now, that's the first block of the first notebook. So any questions so far? Cool. Then I'll continue. Again, if you have questions, feel free to ask them on the Slack channel. I mean, you can use MS Teams as well, but maybe Slack will work better because we can create threads. What I'm going to talk about now is how can we pass options to this model. So right now, when we create our model, we said we want PyBaMM.lithium-ion.dfn, and we didn't pass any options. That means everything by default. But maybe we want to change something. So what I'm going to do now is I'm going to create a model that I'll call it model fast. So it's a separate one, and I don't override the one I had before. And what I'm going to tell PyBaMM is the following. So here, I'll create a dictionary with the options. And you can find the different options you can pass in the documentation. But basically, what I'm going to do say here, I'm going to tell it that for my particle, I want fast diffusion. And what I mean by fast diffusion is that the model of lithium diffusion in the particles is going to assume that that happens very, very fast. So you actually don't need to track what's the concentration at each point, because it's the same everywhere, because lithium moves so fast within the particle that it very quickly spreads homogeneously across the particle radius. And then here I'm going to pass it another option that it's name. This name does nothing on your simulation. It's just that when we plot it, if you see this plot I did here, there is it said red line is Doyle-Fuller-Newman model. Now, because I'm changing Doyle-Fuller-Newman model, I want to give it another name. So when I plot it and compare with the previous one, I'll say, okay, the red one is Doyle-Fuller-Newman model, and the blue one will be the fast DFN. We'll see that in a minute. So that's my new model. And now I've defined it, and it's stored in this variable called model fast. And now I'm going to create a new simulation. Again, that's important not to override the previous one, because if I override it, I won't be able to compare them. So I call it simfast. And that's the simulation same as before, but now we want to simulate the model fast we just defined. Now we just solve it. Again, like before, our simulation.solve. And we can just plot it. Again, that's the default plot, and that's for our model for the fast diffusion. But actually, as I said, the interesting bit would be to compare this model with the standard DFN. So what we can do now is call PyBaMM.dynamicPlot, and notice that I cannot do what I did before of like simulation.plot or simfast.plot, because that means I'm plotting this simulation. Here I want to be able to put as many simulations as I want. And then as in terms of options, again, I'm going to pass a list, and the list is going to be all the simulations I want to plot. In this case, only two, sim and simfast. And what this is going to do is it's going to go into this simulation, it's going to check that it's been solved, and choose this, take the solution and plot it for us. And as I said earlier, you can see now, that's why we gave it a name. The legend is produced automatically, and it tells us the red one is the Doyle-Fuller-Newman model, and the dotted blue one is the fast DFN model we just defined. And of course, we can also tell it which variables we want to plot. So similarly to what we did before, another option we can pass here is a list of variables. So in this case, if we say we want to see only the terminal voltage, we can produce this plot. So as you've seen with, that might have been a bit too fast, but if you just go into the notebook and you check, you'll see that with very, very few lines of code, we were able to run the standard DFN model, and also change some of the features of that model, and then compare and plot on top of each other. So that's quite handy if you just want to plug and play and try different things to see how your model does. Now, it can be all this happen behind the scenes, all the processing of these variables and getting what numbers you need to plot. But it might be that you want to actually see and get the data set of what you're actually plotting. So you can get that as well. And to do so, what you need to find is the solution of the simulation, right? So once you've solved your simulation, there is this solution object that contains all the output of the simulation. So that contains all the data. However, if you just try to see what's in there, you'll find it's this solution structure. And if I actually looked into it, I cannot do it here, but it would be very hard to extract something meaningful because you'll get all these outputs stacked together, but maybe you want the current that requires some post-processing. The good thing is that the post-processing is done for you. So what you can just do is like call solution and then whatever variable you want. For example, here I want time in seconds. And that will create a post-process variable that you can use to extract your data. For example, if you want to see the entries of that, it will tell us that that's an array, and time, as we expect, will go from 0 to 3,600 seconds. So it goes to an hour because it was a 1C discharge. So that would be my solution in time. And similarly, I can extract the same for my terminal voltage, in this case in volts. And again, I can check the entries. So here you got the two arrays that you can store in variables and do anything you want to them. That is the points that you're actually plotting. But the good thing is that these process variables you can easily interpolate within, because maybe we want the solution at a specific time that it's not one of the existing ones in the array. So you can just do here. I'm going to create the same terminal voltage, but now I'm going to store it in a variable here called V, and then I can just say, okay, I want V evaluated at 200 seconds, 400 seconds, 600 seconds, and maybe 800 seconds. And if I hit that, it will give us the time, the potential at the specific times, right? So let's say 200 would lie between these two. So it will be between these two, 3.73, 3.72. Oh, sorry, it's not the same numbers, not the same structure, but basically you could see that interpolated it for us at a time 200 that it wasn't here. It would fall between these two numbers. So that means that if you want to see this data, you can very easily get around with it. And finally, the last bit for this notebook is okay, we got this data, but maybe we want to process it in another software. So how can we store both the simulation and the data? So let's say we create a new model, and the reason to do that, I'm going to overwrite the one I had. And the reason for that is that because I want to store it, I want it to be quite small now, just for the demonstration. So I'm going to use SPM because it's a much smaller model than DFN. So again, I create my simulation. I can do it in the same cell, and I solve it. So I've now have my simulation, and it's with its own solution and so on. So what I can do now is do sim.save and store it. And here I'm going to tell it what's the name of the file where I want to store it. It's going to be spm.pkl. PKL, for those who don't know it, it's this pickle format. Pickle is a Python package that allows you to store in your computer Python variables, right? It would be similar to what you do in MATLAB when you have all these variables and you just do right click and store them to a .mat file. So if I hit that, that will store it, create a new file called spm.pickle, which will live in my home directory. And by home, it's wherever I created my my Jupyter notebook. Sorry, and yeah, there we go. So if now I go back, you'll see that here, this new .spm.pickle appeared. So that's where it lives, in case you need to access it from somewhere else. But the cool thing is that now, just to show that that worked, I'm going to create a new simulation. But that simulation, it's not going to find a model and create a simulation and solve it. I'm just going to load something that I already stored, which in this case is, again, spm.pickle. So notice that this simulation 2 has been created in a much different way than the original simulation, right? So it just loaded it from some model that we stored. So if I now do sim2.plot, as you'll see, it creates a simulation. And notice that I didn't even have to solve it because when the model I stored had already been solved, right? So if you see what I did here, I defined the simulation for the SPM model, I solve it, and then I store it. And now when I load it, it already has the solutions. So that's very useful when you have a simulation that takes quite a long time, and maybe you then want to do some post-processing and you want to do later, and you don't want that every single time you want to do the post-processing, you want to wait, so I don't know, let's say 20 minutes for the simulation to run. And of course, the whole thing, the whole model is not the only thing, the whole simulation is not the only thing you can store. You can store just the solution, for example. So if I now create this new variable called, which is the solution of my simulation, I can just do solution sol, sorry, the new variable I create, .save, and store spm_sol, again, .pickle. And if we go back, we'll see that now we have the SPM solution that has been stored here. Or, and again, what you could do is, to show that that works, is create a new solution that it's basically loading the solution we just stored. And then you just do PyBaMM.dynamicPlot, as we did earlier, and just plot the solution. Notice that because it's not a simulation, we cannot do sol2.plot, because that would only work if what we did before when we had a simulation. That's why we use this dynamic plot function here. As you can see, we get the plot we want. Right, and the last thing I want to show you how you can store it is the data. So imagine you don't want to store the whole solution. You just want specific variable. So I can do save data, and then I'll store it in this pickle form and say I only want the current in amps and the terminal voltage, because maybe I want to go to MATLAB later and do something with this. Sorry, and it looks to have a typo somewhere. Sorry, not save data, right? So that's in pickle, but as I just said, we would like to do something in MATLAB maybe. That wouldn't be that helpful, right? To store it in pickle form. But actually, we can do the same. Actually, let me just copy it, because this save data function also supports CSV. So I can just create a CSV, or I can create a .mat. So you can see you can store your data in all these different formats. And again, if I go back here, you'll see how all these have been created. And yeah, I cannot see directly from here. But if I just, let me show you. If I just open the CSV from my computer. Yeah, sorry, anyway, I cannot show you now, but here is where they are. And then you can just access them on your folder and do whatever you want with them. Right, so that was the longest notebook we have to do because it covered most of the basics. In the next ones, we'll see how we can change parameters or define experiments. But before we go ahead, do people have any questions? Actually, let me check. How is the MS Teams chat and the Slack channel? Right, it seems that there haven't been any questions for a while, so I guess people are following on. So now I'm going to move on to the, as I said, the second notebook, which is rather short. It's this one, the one called 2, compare models. Again, I'm going to do what I did before and create my own notebook and follow. But as you can see, that one is pretty short. But I think it's a very interesting one, because what we'll see here is how can we compare different models. And personally, I think that's a quite cool example, because in many cases we talk about the DFN model and the SPME and SPM. And it's quite useful to see them one on top of each other. So we'll see how this can be easily done in PyBaMM. So as usual, we need to start importing PyBaMM. And then what we're going to do now, instead of saying model equals PyBaMM.lithium-ion, blah, 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 I'm going to create something called models. And that's going to be a list of models. Sorry, I'm going to separate them. You could do it in the same line, but it'll be easier to follow if I do it like that. So the first model in my list, it's going to be the SPM. Second model, the SPME. And probably you guess that the last model is going to be the DFN model. So now I created this list of models. And what I have to do now is just loop through them and create the simulation and solve them. So what I'm going to do first is, sorry, just in case I didn't run it. Yeah, there we go. First, I'll create an empty list where I'll store my solutions. That's called sims. Here's where I store my simulations once I've solved them. And then I just create a for loop. That's standard Python for loop. If you're not familiar with it, you'll check some of the tutorial online for Python, because that's one of the basic functions. So what it's going to do is go through each of the models within this models list. And every time that picks one, it's going to create a model variable. So I can actually use that within my simulation. So basically, you'll go to the first position and say, OK, what's my model now? Oh, the SPM. I'll create a variable called model, which is the SPM one. So then I can easily do what I did before. So I create a simulation. And this simulation is going to take the model that we're using in this iteration. Then we solve the model. And we don't want to plot it yet. We just want to store it. So to store it, what we do is take our list sims and append our simulation. Append what's going to do is just put this simulation at the end. And notice that it's quite important that before appending the simulation, we solve it. So actually what's in this sims list is actually a solved model. So it has all the solutions, so we can then plot them. So if we do that, that might take a bit longer, because basically it's the it will go through each of the models, but because it's a one series charge, it's pretty fast. And then we just do, again, dynamic plot, because we want to compare some of them. And remember that before we passed a list, we did a list of all this. But actually, sims is already a list. So I just pass that. And it will now create a plot. Again, as I said, there is some lag, but just let's go somewhere in between. You can see now it's comparing the single particle model with electrolyte, and the dual Fuller-Newman model. And as you can see, the main difference is we cannot see much difference in the electrolyte concentration or the surface concentrations because of the simulations and the parameter set. But we can clearly see how the single particle model doesn't include any electrode potential distribution over the X variable, neither an electrolyte potential. That's one of the consequences of having only one particle. But the SPME actually captures, and as we can see here, it captures pretty well the DFN model. So as you've seen, that was very straightforward to compare 3 models. And again, this was for the standard models, but imagine you're developing a new submodel, a new electrolyte submodel, and you want to compare with the standard one. Then it would be just you create a model where you compare maybe your SPME with your new model and the SPME with the standard model, and you compare. So that's a very useful, especially if you are developing new models. Right. So as I told you, notebook 2 was quite short. Again, I'll just wait for 30 seconds or so. Feel free to unmute yourself and ask questions if you have any, or otherwise use the Slack channel or MS Teams chat. Right, then I'll move ahead and go into the third notebook, which is about the experiments. If you remember when I was giving the presentation earlier on, I told you that you can actually define your experiment setups in a quite straightforward way. And actually, until now, we've just been using one C discharge. So let's see how we can do something a bit more exciting. So again, I'll start by importing PyBaMM. And now let me define my experiment. So I'll store it in this variable called experiment, and I'll tell it that needs to be a PyBaMM experiment. And the things I need to pass to that PyBaMM experiment is all the steps that I want my experiment to do. So in this example, I'm going to say, fine, I want to start doing a discharge at C/10 for 10 hours or until 3.3 volts. Sorry, 3.3 volts. That would be enough. We can just do that for an experiment. But there's something else we can do. Maybe we say we want to rest for 1 hour after that. And then we want to charge at 1 amp until 4.1 volts. Sorry, it needs to be blank space here. And then I want to hold my battery at 4.1 volts until I go below 50 milliamps. And then I want to rest for another hour. So let's go through each of the steps to show like all the different things you can tell your experiment to do. So you can say charge or discharge or rest or hold. So it depends on what you want to do. If you specify charge or discharge, notice that you can either say your C rate or your current. It doesn't matter. PyBaMM will translate one into the other and run your simulation for you. Also, in terms of the C rate, you can specify it not just C/10. If you said 0.1 C, that would work too. And then you say for how long, right? So for example, here I said for 10 hours. Here I said until 4.1 volts. But notice that you can pass multiple conditions, right? So for 10 hours or until you hit your critical voltage here, 3.3 volts. So as you can see, it's a given language here. So it's not just you can write anything, but it's pretty flexible and it's pretty straightforward to implement. I would say that this example here covers most of the possibilities you have. There is also the potential give it a given power for this chart, so it would be just maybe instead of 1 amp, 1 watt, but pretty much everything is in here. If you want to see the possibilities, you can go to documentation. Again, the link is on our website. And then if you search here for experiment, you'll find the experiments. And then if you just go to base experiment class, here it explains how it's done. So there are a few examples, charge at 1 C for 1 hour. As I said, you can specify amps, C rate, watts. So there's more information here. And the last thing is that imagine that's fine, but I want to repeat this 3 times. So instead of copy pasting it 3 times, I mean, 3 times would be fine, but imagine you want to do it 100 times, you just do times 3. And actually, of course, it doesn't make sense to multiply a string by 3. What PyBaMM does is, sorry, Python does, that's actually a Python thing. It's going to take this list of instructions you define, and it's going to put 3, one after the other. So this way, it's very, imagine you want to define a Git test that's going to have a lot of pulses. That's very straightforward because you just define the structure of 1 pulse and you say how many times you want to repeat it. So I store this experiment in the variable, and then I can just create, again, my model, in this case, the FN model. And I create my simulation. So far, pretty similar to what I did before. I tell it which model I want. But as I said, this simulation does everything by default unless told otherwise. So normally, it shows as the experiment a 1 C discharge until the critical voltage, which is one of the parameters of the battery. But now I'm going to say, no, I want you to run an experiment, and the experiment is the experiment. Actually, that might be confusing. Just let me change how I call it, because here one experiment is the option I'm passing, and the other one is the details of the option. So let's call this one exp, and then I'll just do experiment equals x. Let me run it again. And now my simulation will know that it has to run my model following the steps specified in the simulation, in the experiment, sorry. And again, what we normally do, we solve the simulation and plot. You'll notice that the experiment takes longer to run, and the reason for that is the way it's coded, and also because it will require events in order to catch up when you hit a critical voltage or a critical current. And therefore, if you remember in the slides, there was the Casadi fast and the Casadi safe. The Casadi fast, it's very convenient for 1C because you don't need to look for any events, but now you need to. So it takes a bit longer, but still it's quite reasonable in terms of the computational time. And now I just plot. So you can see now that's the current. You can see now the applied current, which repeated 3 times the whole discharge, rest, charge, hold at a given voltage, and then rest again, and then again you charge. So you repeat that 3 times. And again, you get all the variables. You can play around. As I said, that lags a little bit, and we'll fix it as soon as possible. But you can see how the different variables evolve in time for this profile. So that's the other aspect we wanted to show, which is experiments. And finally, the last one, which is changing the parameters. So as I said, everything runs by default unless told otherwise. So far, we've been using the parameter set that comes by default for this model, which, if I remember correctly, it's the one specified in Marquis et al. 2019. But yeah, in terms of that, let me show you. That's one of the features. I think we're going to talk about it next week, but just to show you. So if you do PyBaMM.print citations at the end of your script, you're going to find all the papers that contributed to the simulation you just run. So for example, here, as I said, we're going to talk more about it next week when you talk about how to contribute to PyBaMM. That's to make sure everyone gets proper credit for their works, right? So for example, here we say we need to cite Marquis 2019 because of the parameters, the Doyle Fuller-Newman paper for the model, Sulzer et al. But because we're using PyBaMM, and then Anderson et al. Because of we're using Casadi as a solver. So yeah, the paper I meant for the parameters is this one. So if you want to check, you can go there. Right. So again, I'm going to give a short pause while I prepare the new notebook. So feel free to ask any questions if you have. Yeah, I'm seeing a comment on that in the in Slack. So all these things is we're using the most recent version, which was released yesterday. So if you installed PyBaMM basically earlier than yesterday afternoon, some of the things might not work. I think the only thing that might break is the interpolation of the voltage that I showed. So if that was why you were getting an error, that's why. Yeah, I think it's the instructions are on Slack on how you can upgrade it. Otherwise, just pause there. Right, so I'm gonna go ahead and do the last notebook, which is the one called changing parameters. So it's notebook 4 in the examples that are up there, right? So this one, parameters. So again, we start importing PyBaMM. And now what we want to do is we want to use another parameter set. We are not just using the one that comes by default, but maybe we want to use another one. So we're going to define a chemistry. And here by chemistry, we mean the whole set of parameters you're using. So of course, anode and cathode chemistry, electrolyte, but also the geometry and a whole set of parameters that we'll see in a second. So next week, we'll show how to put your own in, but there's some parameters already available in PyBaMM. So in this case, you can do all the parameter sets that are available. What I did is type PyBaMM.parameter sets, and then if I just hit tab on my keyboard, you'll find what are the different options, right? So there's the Ecker paper, Marquis 2019 is the one I just talked about, Mota 2020, NCA, Kim 2011 for the NCA, and also Suzo 2019. Though I think this one might be for lead acid. Correct me in the chat or if I'm wrong. But today I want to use this one, Chen 2020, which is a paper that we did in a collaboration between University of Birmingham and WMG on an NMC 811 battery. So I'm going to say that I want this parameter set. And if you now look what this chemistry variable looks like, notice that it tells us all the parameters it's using. So it's saying first chemistry, it's probably ambiguous with the previous naming, but basically means we're using lithium-ion models instead of lead acid. Cell, that's the geometry of the cell. We're using this LGM50 from Chen 2020. Anode, graphite from the same paper. Separator properties. Cathode, again from the same paper. Electrolyte, in the paper, they use these reference for the electrolyte properties. Experiment is actually how you set it up, and it contains as well initial conditions, heat transfer coefficient, and so on, things that are depending on the experiment you're running. SEI properties, even though our model doesn't have it, so this doesn't matter. And finally, what's the citation? So that will make sure that when I run that command I ran earlier about print citations, this paper will come up and say, hey, you need to cite this paper because you use those parameters. And of course, you could just change any of those to your own or to another existing one. But we'll see that how to do that in one of the case studies next week. So now what I'm going to do is create my parameters. And to do that, I'm going to say PyBaMM parameter values. So it pulls the parameter values from a given chemistry. And now I need to specify which chemistry. So again, chemistry. And yeah, to avoid chemistry, let's do my chemistry here. So it's clear what is actually what we're passing and what is actually an option. So now if we call what params is, you'll find all the parameters we're actually using. And that's a pretty long list. It's like the variables list I had in the first notebook. So you get all of them here. Some of them are just numbers. Fine. Some of them you'll find they are a function. That's because it says function, electrolyte conductivity, Nyman 2008. We'll find next week how to go and find this function, but basically it means that this parameter actually depends on some variables, and how this happens is defined in a file in the parameter structure. And you can even get, for example, for the OCVs, an array of data sets, data points. So if you remember earlier, we said that the parameters can be specified, the ones which are functions can be specified directly from data. So that's what happens here. PyBaMM takes this data set and knows that we'll have to interpolate through these points. So that's pretty long. And again, we might want to find a specific one. So we can do search similarly to we did earlier with the variable. So params, sorry, it's in plural, params.search electrolyte. And that will throw all the parameters that have electrolyte in the name. And then it's much easier to see what you're looking for. So here we see the electrolyte, the conductivity and diffusivity, they are defined as functions. What's the initial concentration, Bruggemann coefficients, and the typical electrolyte concentration. And now that we have these parameters, we can change a specific one. So let's say we want to change the current function. So what's going to be the current, by current function, we mean what's the applied current in which you do your discharge. So right now, that is 5 amps. That's the 1C current. But let's say we want to do it at a 2C, which of course we could use an experiment, but we can do it here as well. So we say now my current function, again, params, there's a typo here, will be 10 amps. And if I now ask, okay, what's your current function now? It should throw that now it's 10. So now I can go ahead and run my simulation. So let's say model, I'll use SPME now because I haven't used it before. So now we've seen all the different models. And I create my simulation. And again, like we did with the experiment, we need to say what are the things that are not optional. So in this case, the parameter values need to be the ones in params. So if we now solve the simulation and we plot it, we'll see, we'll get our simulation results from this parameter set. And as you can see, for example, here, we ask a C rate that was about 2C, so it discharged in about half an hour, which makes sense. But that's not the only thing you can do. I mean, of course, you can change any of the parameters here. The reason we chose the current function is because that one has more features, such as running a drive cycle that's provided from data. So what we can do now is, again, we change what's the current function that we want to use in our simulation, and we say it's current data. We put that between square brackets because that's to tell PyBaMM that's not a number. It's just you need to look for the data sets that are inbuilt in PyBaMM. And again, the way you pass them, if you want to add new ones, it's the same way as you pass new parameters, which we'll see next week. And then you say US06, that's one of the ones that come by default in PyBaMM. So now, and that's important, I need to create the model again, because what happened is that when we solved the model, some things were modified in place. So the parameters were already put in. So if we just create a new simulation and solved again, what we would find is that the current data has not been updated. And then again, we can create a simulation with model, which has now will be this one that has been updated, and the new parameter values. We solve the simulation and we plot the simulation. And you'll notice that the simulation here takes longer because as we saw when we compared the solving times, actually drive cycle takes longer to run. And now to plot, I'll just show current and terminal voltage. So it's more obvious what's going on with the drive cycle. So as you can see, that's the drive cycle we put in, and that's what the voltage we have. So that's the second way you can pass your input current as data points for the drive cycle. Or alternatively, you can define your own function of time and say, look, I want you to follow that function. So to do that, we have to import NumPy to use, and then we define a function that we'll call it myCurrent, which is a function of time, and basically returns sine profile. Before running this, let me comment on a few points. Notice that sine here, we use the sine function defined in PyBaMM rather than the one defined in NumPy. The reason for that is that if we use this one, PyBaMM knows how to calculate the derivatives and so on, so it will help calculating that Jacobian that we use to run faster. So now that we have this function, what we can do is define the current function, and we tell it that we want it to be myCurrent. And again, I'm going to copy these lines here because we want to create a new model. So we make sure that anything that we overrode when we ran the old parameters is gone, and we create a simulation. And now there are two things you can do. We can pass a time vector so we know which points to evaluate. So we know that the resolution is good enough for our plots. So what we're going to do is use this NumPy A range, basically creates an array with a given range. So it goes from 0 to 1 to 1, to 1 in 121 steps. And then we just solve the simulation. And now we say, I want you to use this time here. And again, that runs the simulation. And we can just do, again, plot the current and the terminal voltage. And as you can see, you get this nice sine wave, which translates into these sinusoidal oscillations in the terminal voltage. So basically, these are the three, apart from experiments, which calculates what's the current profile you pass through without you worrying about it. There are three ways you can pass your input current. You can just say a fixed one, so you just throw a number in. You can pass it from data, and that's the easiest way to get drive cycles through, because PyBaMM will do the interpolation for you. Or you can just define your own functions. And the last thing I want to show, and again, that's related to what we're going to do next week, is this. Don't worry too much about the syntax. Basically, that means that should be run in your terminal. But there is a command, and again, we'll talk in detail about that and how to use it next week, which says, which is going to call you what are the parameters you want to use, right? So it says, what this does is copy the whole parameter set that it's hidden somewhere on the PyBaMM package into your home directory, wherever you define your notebook. So if I now go here, notice that there is this folder here called lithium ion, and then you can check all the parameter sets you have. So notice that these match the different fields we got in our chemistry. And if I just go to cathodes, here you get the different folders. Let's see, from Chen 2020, you have all the parameters here. You have a README with information on which paper come from and some comments, the data for the OCV as a CSV, and for example, the NMC electrolyte exchange current density defined as a Python function. So remember, when I call the parameters and somewhere defined as functions, where here is where the functions are defined. But again, more to follow on that in one of the case studies next week. So that's basically all we wanted to cover for today's session. We still have 10 minutes, so feel free to ask any questions. Just to say that for next week, we suggested a couple of exercises that you can do to explore PyBaMM a bit further. Of course, there are all the examples here you can find in our website. So you can try to modify them to do something you're interested in. But if you are not inspired on what to do, we suggest here a couple of examples. One of them is try to run a Git test, which seed rate and duration of your choice for two different parameter set, and then compare the output. So get a plot with the two outputs, the two solutions on top of each other. Or investigate how the agreement between the SPM and BFN varies as you change the applied current. And of course, if you get stuck, you can ask for help on Slack, and there'll be someone around to help you. And if you like a new feature or you find a bug and you want us to be aware of that, create an issue on GitHub. So you go to our GitHub repository. I think you all have the link. You click to issues and you open a new one saying if you want a new feature and so on. You can also check what are the things that we have in the pipeline to implement in terms of existing issues. So that's everything. And yeah, feel free to unmute yourself and ask questions if you want. By the way, just let me show you something in terms of the examples. So let me go to examples of PyBaMM.org. There are two types in terms of notebooks, as we've seen, but there are also scripts. So everything we've shown is in terms of Jupyter notebooks, but of course you can define your own scripts. So for example, yeah, you can use your own coding editor to run it, and then that's another option. Just to mention that you don't have to do everything on Jupyter notebooks. Cool. So if there are no questions at the moment, I think we can finish the seminar here. But again, if you have any questions during the week while you're trying the exercises or so, you can just drop a question in the Slack channel, the one for the Faraday Tech series, and yeah, we'll be happy to help on that. Just the last ad for me is that the upcoming sessions for the Faraday Tech is the one on 4th of June on IP. There's going to be the second part of PyBaMM next week on 9th of June, same time. And on the 11th of June, there's the second session on IP, in this case from a commercial perspective. So thanks for joining today.
Thank you.
Thanks, Farah.